The NEC, or National Electrical Code, has specific requirements for tap conductors, especially within control enclosures. The purpose of these rules is to ensure electrical safety and prevent overcurrent situations that could lead to fires or equipment damage. In a control enclosure, a tap conductor is a conductor that branches off from a main feeder conductor to supply power to a specific component, such as a motor starter, a control transformer, or other control devices. The NEC addresses tap conductors in Article 240.21, which provides the general requirements and then has specific exceptions that allow for taps in certain situations. The fundamental principle is that tap conductors must be protected against overcurrent. This protection is typically provided at the point where the tap originates from the feeder. However, the NEC recognizes that in certain cases, it's acceptable for the overcurrent protection device to be located further downstream from the tap point, provided certain conditions are met. One of the most common tap rules relates to the length of the tap conductor. The general rule is that the tap conductor should not exceed 10 feet in length, and it must be enclosed in a raceway or otherwise protected from physical damage. However, there is also a specific rule that applies to taps within control enclosures, sometimes referred to as the 6-inch tap rule. This rule allows for shorter tap conductors within a control enclosure without requiring overcurrent protection at the tap point, provided that the tap conductor meets specific requirements. The 6-inch tap rule essentially states that if the tap conductors are located within a control enclosure and do not exceed 6 inches in length, then overcurrent protection is not required at the point where the tap originates. The reason for this exception is that within a control enclosure, the conductors are generally well protected and the risk of physical damage is reduced. The primary requirements for complying with the 6-inch tap rule are: firstly, the tap conductors must originate within the control enclosure. Secondly, the tap conductors must not exceed 6 inches in length. Thirdly, the ampacity of the tap conductors must be at least equal to the calculated load they will serve. And fourthly, the tap conductors must terminate in a single overcurrent protective device. The NEC defines a control enclosure as an enclosure containing control equipment, such as motor starters, push buttons, relays, and other control devices. The enclosure provides protection for the equipment and also helps to prevent accidental contact with energized parts. When applying the tap rules within a control enclosure, it's essential to carefully consider the location and length of the tap conductors. If the tap conductors exceed the 6-inch limit, then overcurrent protection must be provided at the tap point, or the tap conductors must comply with one of the other tap rules in Article 240.21 of the NEC. One common mistake is to assume that the 6-inch tap rule applies to all taps within a control enclosure, regardless of their length. However, if the tap conductors are longer than 6 inches, then they must comply with one of the other tap rules, such as the 10-foot tap rule or the 25-foot tap rule, depending on the specific application. Another important consideration is the ampacity of the tap conductors. The ampacity of the tap conductors must be sufficient to carry the load they will serve. If the tap conductors are undersized, they could overheat and create a fire hazard. To determine the appropriate ampacity for the tap conductors, you'll need to calculate the load they will serve. This calculation should take into account the rating of the equipment connected to the tap conductors, as well as any applicable directing factors for ambient temperature or the number of conductors in a raceway. In addition to the length and ampacity requirements, it's also important to ensure that the tap conductors are properly installed and protected from physical damage. This typically means enclosing the tap conductors in a raceway, such as conduit or electrical metallic tube ENT, or using appropriately rated cable. The raceway or cable should be securely fastened to the enclosure and to the equipment being served by the tap conductors. When working with tap conductors in a control enclosure, it's always a good idea to consult with a qualified electrical inspector or engineer to ensure that the installation complies with all applicable NEC requirements. The NEC can be complex and difficult to interpret, and it's important to get it right to ensure electrical safety. To further elaborate on the application of the NEC tap rules within a control enclosure, it is crucial to understand how these rules relate to overcurrent protection and conductor ampacity. The fundamental principle behind overcurrent protection is to protect conductors from overheating due to excessive current flow. This protection is typically provided by circuit breakers or fuses, which are designed to interrupt the flow of current when it exceeds a predetermined level. In the case of tap conductors, the NEC recognizes that it may not always be practical or necessary to provide overcurrent protection at the point where the tap originates. This is especially true in control enclosures, where space is often limited and the tap conductors are relatively short. However, to ensure safety, the NEC imposes strict requirements on the length and ampacity of tap conductors that are not protected at their point of origin. The 6-inch tap rule, as discussed earlier, is one example of this. Another common tap rule is the 10-foot tap rule. This rule allows for tap conductors to be up to 10 feet in length without overcurrent protection at the tap point, provided that certain conditions are met. Firstly, the ampacity of the tap conductors must be at least 1/3 of the ampacity of the feeder conductors from which they are tapped. Secondly, the tap conductors must terminate in a single overcurrent protective device that is rated no higher than the ampacity of the tap conductors. Thirdly, the tap conductors must be protected from physical damage. If these conditions are met, the 10-foot tap rule can provide a more flexible wiring solution than the 6-inch tap rule, especially in situations where the equipment being served by the tap conductors is located some distance from the feeder conductors. There is also a 25-foot tap rule. This rule allows for tap conductors to be up to 25 feet in length without overcurrent protection at the tap point, provided that even stricter conditions are met. Firstly, the ampacity of the tap conductors must be at least 1/3 of the ampacity of the feeder conductors from which they are tapped. Secondly, the tap conductors must terminate in a single overcurrent protective device that is rated no higher than the ampacity of the tap conductors. Thirdly, the tap conductors must be protected from physical damage. Fourthly, the tap conductors must be installed in a raceway or otherwise enclosed for their entire length. Fifthly, the tap conductors must be located in a high bay manufacturing facility where only qualified personnel have access. The 25-foot tap rule is typically used in industrial settings where it is necessary to run tap conductors over long distances to serve equipment located throughout the facility. When applying any of these tap rules, it is essential to carefully consider the ampacity of the tap conductors. The ampacity of a conductor is its current carrying capacity, and it is determined by the size of the conductor, the type of insulation, and the ambient temperature. The NEC provides tables that list the ampacity of various types of conductors under different conditions. When selecting tap conductors, it is important to choose conductors that have sufficient ampacity to carry the load they will serve. If the tap conductors are undersized, they could overheat and create a fire hazard. In addition to the ampacity of the tap conductors, it is also important to consider the voltage drop across the tap conductors. Voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for power circuits and 5% for lighting circuits. To minimize voltage drop, it is important to choose tap conductors that are large enough to carry the load and to keep the tap conductors as short as possible. When working with tap conductors in a control enclosure, it is also important to consider the grounding and bonding requirements of the NEC. Grounding is the process of connecting electrical equipment to the earth, which provides a path for fault current to flow back to the source. Bonding is the process of connecting different metal parts of the electrical system together to create a low impedance path for fault current. Proper grounding and bonding are essential for electrical safety, as they help to prevent electric shock and reduce the risk of fire. The NEC provides detailed requirements for grounding and bonding in Article 250. When installing tap conductors in a control enclosure, it is important to ensure that the enclosure is properly grounded and that all metal parts are bonded together. This can be accomplished by using grounding bushings, bonding jumpers, and other approved methods. In summary, the NEC tap rules are designed to ensure electrical safety by protecting conductors from overcurrent conditions. When applying these rules within a control enclosure, it is important to carefully consider the length, ampacity, and insulation of the tap conductors. It is also important to comply with all applicable grounding and bonding requirements. By following these guidelines, you can ensure that your electrical installations are safe and compliant with the NEC. Furthermore, it is imperative to understand the specific definitions and terminology used in the NEC related to tap conductors and overcurrent protection. For instance, the term overcurrent encompasses both overload and short-circuit conditions. An overload occurs when the current in the circuit exceeds the rated ampacity of the conductors, but the impedance of the circuit remains relatively high. A short circuit, on the other hand, occurs when there is a low impedance path for current to flow, resulting in a very high current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect against both overload and short-circuit conditions. Circuit breakers typically use a thermal element to detect overload currents and a magnetic element to detect short-circuit currents. Fuses, on the other hand, use a fusible link that melts when the current exceeds a certain level. The NEC also distinguishes between different types of overcurrent protection devices. For example, inverse-time circuit breakers are designed to trip faster as the current increases, while instantaneous trip circuit breakers are designed to trip almost immediately when a short circuit occurs. The type of overcurrent protection device that is required for a particular application depends on the specific characteristics of the circuit and the equipment being protected. Another important term to understand is ampacity. As mentioned earlier, ampacity is the current carrying capacity of a conductor. The ampacity of a conductor is determined by its size, the type of insulation, and the ambient temperature. The NEC provides tables that list the ampacity of various types of conductors under different conditions. These tables are based on extensive testing and engineering analysis, and they are designed to ensure that conductors do not overheat and create a fire hazard. When selecting tap conductors, it is crucial to choose conductors that have sufficient ampacity to carry the load they will serve. This requires careful calculation of the load and consideration of any applicable dirty factors for ambient temperature or the number of conductors in a raceway. In addition to the ampacity of the tap conductors, it is also important to consider the voltage drop across the tap conductors. Voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for power circuits and 5% for lighting circuits. To minimize voltage drop, it is important to choose tap conductors that are large enough to carry the load and to keep the tap conductors as short as possible. It is also important to use conductors with low resistance, such as copper conductors. When working with tap conductors in a control enclosure, it is also important to consider the grounding and bonding requirements of the NEC. Grounding is the process of connecting electrical equipment to the earth, which provides a path for fault current to flow back to the source. Bonding is the process of connecting different metal parts of the electrical system together to create a low impedance path for fault current. Proper grounding and bonding are essential for electrical safety, as they help to prevent electric shock and reduce the risk of fire. The NEC provides detailed requirements for grounding and bonding in Article 250. When installing tap conductors in a control enclosure, it is important to ensure that the enclosure is properly grounded and that all metal parts are bonded together. This can be accomplished by using grounding bushings, bonding jumpers, and other approved methods. In addition to the technical aspects of tap conductors and overcurrent protection, it is also important to be aware of the legal and regulatory requirements that apply to electrical installations. The NEC is a consensus-based standard that is developed and maintained by the National Fire Protection Association (NFPA). However, the NEC is not a law in itself. It is typically adopted by state and local jurisdictions as part of their electrical codes. These codes have the force of law, and they must be followed by all electrical contractors and installers. It is important to be familiar with the electrical codes that apply in your jurisdiction and to ensure that all electrical installations comply with these codes. Failure to comply with electrical codes can result in fines, penalties, and even criminal charges. It is also important to be aware of the licensing requirements for electrical contractors and installers in your jurisdiction. Most jurisdictions require electrical contractors and installers to be licensed, and they may also require them to pass an examination to demonstrate their knowledge of electrical codes and safe work practices. When hiring an electrical contractor or installer, it is important to verify that they are properly licensed and insured. This will help to protect you from liability in the event of an accident or injury. In conclusion, the NEC tap rules are designed to ensure electrical safety by protecting conductors from overcurrent conditions. When applying these rules within a control enclosure, it is important to carefully consider the length, opacity, and installation of the tap conductors. It is also important to comply with all applicable grounding and bonding requirements. By following these guidelines and being aware of the legal and regulatory requirements that apply to electrical installations, you can ensure that your electrical systems are safe, reliable, and compliant with the NEC. To expand on the practical implications of applying the tap rules, consider specific scenarios within a control enclosure. Firstly, a scenario may involve a control transformer that requires a tap from a main feeder. The transformer is used to step down the voltage to supply power to control circuits. If the distance from the feeder to the transformer is less than 6 inches, the 6-inch tap rule can be applied, and no additional overcurrent protection is needed at the tap point, provided the other conditions are met, such as proper conductor ampacity. Secondly, a scenario may involve multiple control devices, such as motor starters and relays, each requiring a tap from the main feeder. If the distances to these devices exceed 6 inches, the 10-foot or 25-foot tap rules may be applicable, depending on the specific installation conditions. In this case, the tap conductors must be sized appropriately, protected from physical damage, and terminated in a suitable overcurrent protection device. Thirdly, a scenario may involve a complex control system with numerous components and interconnections. In this case, it is essential to carefully plan the layout of the control enclosure to minimize the length of the tap conductors and to ensure that all applicable NEC requirements are met. This may involve using raceways to route the tap conductors, selecting appropriate overcurrent protection devices, and providing adequate grounding and bonding. When designing and installing control enclosures, it is also important to consider the environmental conditions in which the enclosure will be used. For example, if the enclosure will be exposed to moisture, dust, or corrosive substances, it may be necessary to use a NEMA rated enclosure that provides additional protection. The NEMA rating system classifies enclosures based on their ability to protect against various environmental conditions. For example, a NEMA 4 enclosure is designed to be watertight and dust-tight, while a NEMA 4X enclosure is designed to be watertight, dust-tight, and corrosion-resistant. In addition to the environmental conditions, it is also important to consider the temperature range in which the enclosure will be used. Electrical components are typically rated for a specific temperature range, and it is important to ensure that the temperature inside the enclosure does not exceed these limits. This may involve using ventilation fans or air conditioners to cool the enclosure, or using heaters to warm the enclosure in cold environments. When selecting electrical components for a control enclosure, it is important to choose components that are UL listed or otherwise approved by a recognized testing laboratory. UL listing indicates that the component has been tested to meet certain safety standards. Using UL listed components helps to ensure that the control enclosure is safe and reliable. It is also important to follow the manufacturer's instructions when installing electrical components. The manufacturer's instructions typically provide detailed information on how to install the component properly and safely. Failure to follow the manufacturer's instructions can void the warranty and may also create a safety hazard. In addition to the NEC and UL standards, there may be other applicable standards and regulations that apply to control enclosures, depending on the specific application. For example, if the control enclosure is used in a hazardous location, it may be necessary to comply with the requirements of the National Electrical Code Article 500 through 516, which covers hazardous locations. Hazardous locations are areas where flammable gases, vapors or dust may be present. Control enclosures used in hazardous locations must be designed and installed to prevent the ignition of these flammable materials. This typically involves using explosion-proof enclosures, intrinsically safe circuits, and other special precautions. In conclusion, the design and installation of control enclosures is a complex process that requires careful attention to detail and a thorough understanding of the applicable codes, standards, and regulations. By following the guidelines outlined in this discussion and consulting with qualified electrical professionals, you can ensure that your control enclosures are safe, reliable, and compliant with all applicable requirements. Remember always to prioritize safety and consult with qualified professionals when working with electrical systems. The information provided here is for educational purposes and should not be considered a substitute for professional advice. Always follow the applicable codes, standards, and regulations in your jurisdiction.